All right, well, I can introduce our speaker then. It's my pleasure to introduce our visitor, Ioannis Brilakis, who's coming from Cambridge by way of Munich. Did I get that right? He's the Lang O'Rourke Lecturer in Construction Engineering at the Department of Civil, Structural, and Environmental Engineering at the Department of Engineering in the University of Cambridge. He's got his PhD from UIUC and had a faculty job in Ann Arbor at Georgia Tech and now is in the UK. So without further ado, I'll hand it off to our speaker here.
All right, thanks, Justin. So first of all, hello everyone, and thank you for coming to this presentation. A very small, tight audience today, but I think that's even better. We can also have more of a conversation rather than a direct presentation. And thanks also to Justin and Eva who organized it. So yeah, for those of you who don't know me, my name is Ioannis Brilakis. I'm a reader at the University of Cambridge, the engineering department. And I'm here today to talk to you about virtualizing infrastructure. So let me first define the title. Let's start with the easy one. Infrastructure here, we mean what civil engineers do. I come from civil engineering, by the way, disclaimer. So you will see more of a civil engineering presentation rather than a computer science presentation. It's a different perspective. So infrastructure here, we're talking about buildings, bridges, tunnels, roads, rather than, for example, cyber infrastructure or things like that. By virtualizing, I'm referring here to the process opposite to construction. So in construction, what we do is we go from an architectural model to a real thing. Well, here I'm trying to do the opposite. Can I go from the real thing to a virtual copy of that real thing? That's something that we call the digital twin. I'd like to start first with a short introduction to the place I come from. Cambridge. It's quite an old place. Was founded in 1209 and granted royal charter by King Henry III. It's the world's fourth oldest university with over 31 colleges and about 100 academic departments organized in 6 schools. It operates Cambridge University Press, which is the world's oldest publishing house, 8 museums, a botanic garden, and a library with 15 million books. And the university itself has, I think, a research income of about £2 billion and an endowment together with the colleges of about 6 billion, making that the largest outside of the United States. On top of that, university has about 7,000 academic staff and maybe about 20,000 students. It's consistently ranked, thank you, Eva, within the top 3 or 4 universities around the world overall, as well as in various disciplines. And here you see some pictures from the university. I think I have here Corpus Christi, King's, and Trinity. The picture you see from Trinity, presumably this is a tree, an apple tree, which is a descendant of Isaac Newton's apple tree, planted in front of his office at Trinity College. Speaking of Isaac Newton, the university has educated many notable alumni, including eminent mathematicians, scientists, politicians, philosophers, and heads of state. People like Charles Darwin, Niels Bohr, Alan Turing, George Stokes, John Harvard, who later came over to this side and established a school down the street, and several others, John Maynard Keynes, our recently departed Stephen Hawking, various royalty like King Edward VII, King George VI, Queen Margaret II, and so on and so on. Overall, the university has been the home to 78 Nobel laureates, the most of any university in the world, as well as 15 British prime ministers and 10 Fields medalists. And next to it, it operates what we call the Silicon Fen, which is our high-tech business cluster with 25,000 companies that have around the world 200,000 staff and have an annual turnover of roughly £36 billion. But of course, the most important thing that we always like to mention is that we beat Oxford in both the men's and women's boat races this year. And I think that's important that it exists in every one of our presentations. So moving closer to home, the Department of Engineering at Cambridge integrates all of the engineering divisions in a single unit with a single undergraduate degree. So we have a BA in engineering. And the civil division of that, the area that I'm in, sits within the National Center for Smart Infrastructure and Construction and is home to the Lengeruk Center for Construction Engineering and Technology. My group, the Construction Information Technology Lab, is part of that center and closely linked with the University Center for Digital Build Britain. It is a research lab oriented on advanced applications of computer vision and pattern recognition on infrastructure data collection, information retrieval, and knowledge generation. So I'll stop with the introduction here and move on to what we're actually doing, the research. The construction sector has a massive productivity problem. As a sector, we are outperformed by just about everyone else in the global economy in value added per man hours, which leads to substantive value lost across the spectrum, everywhere in the globe, and particularly in developed economies. Of the 4 key trends that can disrupt this phenomenon, only one is technical. New technologies, digital technologies, new materials, and advanced automation. The problem that we have with this is that how can we exploit these things, digital and automation technologies, without first digitizing our processes and hence our products? If you look at how we are doing in terms of digitization within the construction sector, we are almost the worst. Only agriculture and hunting is below us. And this is before we actually are at the very bottom of all industries in terms of data stored. We basically lack the efficient means to cost-effectively generate and exploit what we call digital twins of our assets, which is why only less than 2% of the existing building stock even has a basic design information model of any sort, and even less for horizontal infrastructure. This is the problem that my group at Cambridge is focusing on. But before I tell you how we solve it, I want to tell you first what the outcome looks like. Define the digital twin. For manufacturing, this is not a new expression. It's been around for a while. For civil engineering, it is a rather new expression. Yes, it is a model. It's a digital copy of a real thing. But what makes it different than all the other models is 2 aspects. One is replication. It has to accurately replicate the real world, both in terms of geometry and other aspects. And the second bit is connectivity. It has to be connected ideally to the real asset so that we can see, hear, and feel exactly what the asset is experiencing. Likewise, a national digital twin is an ecosystem of digital twins connected via securely shared data. And the table that you see here in the bottom is the Gemini principles that will soon be published by the UK's Digital Framework Task Group, which basically explain what we need to do to ensure that we have reliable digital twins that can be used to manage and operate infrastructure. So, in a nutshell, what we try to do is we try to create geometric digital twins of buildings and infrastructure, enrich them with structured and unstructured data, and then exploit them to improve design, construction, and operation processes. So the example you see here, I want to automatically somehow scan this bridge in some way, get the points and the pixels. From these, convert them into actual objects of an information model, and then add the real textures on top, detect and measure, for example, any visible condition data, and assign these things as properties to the object, ideally with little or no human input. And of course, I then want to exploit this outcome. So here's how we do that. I'll start first with some work we've done quite a lot of years back. This is work we finished in 2012 on what we call mid-range mobile videogrammetry. Back then we were trying to scan buildings with laser scanners, and it would take us quite a lot of time to finish scanning sessions, given the time it takes to produce each scan and the fact that you have to scan separately in every single room if you want to produce a complete model. At the same time, I was exposed to several medical tools that allow you to scan a human body interactively, which was pretty cool. The problem is that we couldn't use those tools for civil infrastructure because we had long scanning distances. I had to be able to do that scan from, let's say, 25 meters away. So what we did at the time is we came up with a modification to the hybrid bundle adjustment, to the bundle adjustment process used in photogrammetry, to add on top of it not just point features optimization, but also lines and plane features, which are actually very, very strong in infrastructure. The consequence of that is we were able then to come up with a solution that allows you to take your phone out, videotape a building from 25 meters away, and from that create a point cloud with a sub-centimeter spatial error. Now that's all great, and then you can use additional techniques to fill the gaps, equalize the densities, fix the holes, and so on. But for us, that's still just a point cloud. It's the beginning of a journey rather than the end. Engineers, at least our kinds of engineers, don't like to play with points. They like to play with models. And so our next challenge was, how do I go from a data set like a point cloud, which is primarily meant for the computer's eyes to see rather than a human's eyes, into something that engineers are more easily familiar with, like the models you see here. That's actually a much bigger challenge. And it's a much bigger challenge for a couple of reasons. First of all, because we're talking about a massive labor task to create the models. For example, for every 1 day of laser scanning, many sources report you need to spend 10 days modeling. The example you see here in the picture, a reactor building 40 billion points, it took 10 people 6 months to make the model. This is from Eva's research. The other problem is that we're looking at massive point clouds that we cannot open with a single computer in many cases, with well above 30 billion points. And for example, in large industrial facilities, we easily exceed 100 billion points. We can only open them piecewise, try to model, and then try to stitch the results together at this point. But the worst problem of all is what I call modeler fatigue. It's a boring job. Can you imagine someone modeling pipe after pipe, valve after valve? We're talking about tens of thousands of objects, in some cases hundreds of thousands. This is clearly a type of a problem that screams for automation. So a long time ago, we started with very simple methods to try to solve that. This was a very simple columns detector, a work one of my earlier students did, simply being able to walk around and detect columns in real time as you're browsing through buildings. Zoom in 10 years later, now we have the ability, for example, in the case of bridges, to scan a bridge and then from that scan automatically create the components, and then from these components use them for various purposes. What I think is very important to mention here is that we can do this with real data, not synthesized, idealized data. No bridge is straight. No bridge component is straight. In the real world, we have to deal with all sorts of peculiarities and skews. And our ability in this case to use recursive slicing techniques and others allow us to cover these complexities and be able to produce reliable models at the end of the process. In a nutshell, we can go from this to the point clusters to the model without a human interfering in the process. Same thing for buildings. There was another project we did several years back, funded by the European Commission together with Stanford, Georgia Tech, and other universities, to do what we call formalize the digital twin generation process, or in more colloquial terms, how do I go from a video file to an information model. In this case, we looked at similar techniques as we had used in the case of bridges, basically a top-down hierarchical segmentation process. Only in this case it was a bit more difficult because in bridges everything is exposed, whereas in buildings we try to hide everything. In many cases we only see part of the object, and it's very difficult to understand what it is just from what we're looking at. So in those cases we have to infer what might be in the back. Just to explain here with a little bit more detail what kind of strategies we're looking at. In the case of a building, what I'm trying to do is I'm trying to use architectural priors, knowing how a building typically looks like, to try to hierarchically segment it. For example, I know a building has floors, so my first job is to segment the floors. Once I have the floors, then I know that every floor is composed of rooms. And what is a room in a point cloud? It's a big empty blob, right? I want to find those big empty blobs and understand the spatial topology and where the rooms are. Once I know I'm in a room, I can safely assume that most likely there is a ceiling above me, most likely there is a floor below me, most likely that there are walls around me, and so on. I think you get the point. It's a hierarchical process that uses these types of architectural priors to help you understand your environment. This is exactly what you see here of how we use various deep learning tools to go from the big point cloud down to rooms, and then from rooms to detecting slabs, even at the presence of clutter, and then going from that into detecting walls, fitting components there, and then once I have the model, actually detecting the spaces. But of course, geometry isn't everything in our case. We need to go beyond that. And that's the case of enriching that basic geometric digital twin. In our case, we tried to do two kinds of enrichment. One was with condition data. The other one was with sensor data. In the case of condition data, we looked at adding the textures on top of the components. For example, in the case of bridges, measuring on those textures the visible defects, and then assigning those measurements as properties to the model for the types of defects you see in the slide. We tried to do the same, by the way, for the case of roads. This is another project we finished a couple years back. The difference here is that we simply use your parking camera. As you're driving forward, we're capturing the cracks, the patches, the potholes, the various types of defects, classify them separately, measure them, and then it is those measurements that we send back to a local council to help us maintain the roads as an outcome of this process. And you can see here the process behind that. If you want, we can talk about that in more detail later. Another example was with sensor data, as I mentioned before. A digital twin is not complete without connecting it to the physical twin. But to do that, I have to be able to bring sensor data in the model. I have to be able to model the sensors themselves. So we created what we call an IFC data model extension that allows you to place those sensors on the components. And the second thing is to bring the time series data that come in from the sensors and show them, visualize them on the actual geometry. What this allows us to do is what I call the live digital twin, okay? The connected model, where now I can tether it to the physical structure, and as a consequence to that, I can actually monitor the stresses and all the kinds of problems that it feels during its lifetime. The long-term goal is what we call in the UK the national digital twin. I want to be able to go to the point where every single asset of the country is digitized, where I have access to various levels of detail for various types of applications, and I'm able to cross-correlate data from across the different boundaries and use that to predict what might be happening in the next case. The last part I want to talk about is how we exploit these models. What can we do with them? We put in so much effort to create them. Where is the value? Okay? So I'll present here a few examples. This is more applied work. One had to do with the design phase. This is a project we did with Len Goruk, a contractor in the UK, as well as Tony G, a bridge designer. This was in relevance to a major project in the UK called High Speed 2. This is a project that connects London with Birmingham, and it has roughly about 300 bridges and about 100 tunnels. Can anyone guess here what these 300 bridges have in common? So what they have in common is that none of them are iconic. None of them are anything special. Typical highway overpasses that you want to build on time, on budget, maximum certainty, and minimum disruption, which makes the concept of design for manufacturing and assembly very attractive. But for us to employ that in civil engineering, that's very difficult. We're used to designing and delivering bespoke bridges rather than standardized components that can be produced in the factory and delivered on site. So what we did to help bring this concept, as we call it DFMA, into the design phase, is we mapped the entire decision-making process from route alignment all the way to delivered bridge. We mapped every piece of data you need to make each decision, and then we linked those decisions together and started reorienting them so that every time you make a decision, you have exactly the information you need to do that reliably. The second bit that this allowed us to do is it allowed us to understand what are the dependent variables and the independent variables of this process. For example, in a typical highway overpass, the number of independent variables was something like 16. Okay, a very small number of things you can actually affect. But by knowing that, we were able to create this solution here. Basically, our work was all the red arrows connecting this ecosystem, which now allows, in this case, the bridge designer, Tony G, to sit together with the client, ask them those 16 questions, put in the numbers in the system, click a button, here's the final bridge design. That saves them about 7 weeks of work for every iteration. Okay, they can finish 7 weeks in 2 minutes. So they can actually sit with the client and repeat that process as many times as they want to see what would happen if I change this variable and that variable within the various scenarios.
So geography doesn't matter at all? I would imagine there's some work that you need to connect the bridge to.
Oh yeah, it's one of the independent variables, the topography of the environment.
And there's a number or a map, or what does that look like?
It is a digital terrain map that can be used in this process. Another application, moving on to the construction phase, was taking the digital twins into mixed reality and using them for exploring construction progress in this case. The model that you see is a schedule-loaded model. The components that you see were all supposed to have been built at the time that you see this video. Now that I've told you that, you can see that this project's behind schedule because a lot of the components are missing. Well, once you can do that, then you can do a very simple volumetric comparison and immediately update your progress data by telling the inspector everything that you see here in green, that's fine, that's completed. Everything that's red, well, that's something you should have actually done already and you haven't. Very simple application. Another example has to do with monitoring in a factory. What you see here is a vision tracker we created that considers also elements about the worker's process to make the vision tracking a lot more reliable. You can see that even when we see just a little bit of that person, we can still track him. And if he disappears and then returns, we can then recapture him and assign the same ID. For the purpose of creating the spaghetti diagram of motions you see on the right, and then using that in relevance to the component he's actually making in the digital twin to measure productivity. It also allows us to understand the process itself. If I see a lot of repetitions in the moves and stops that he does that are regular, then I'm expecting him to make good progress. Whereas if I see an irregular pattern, then I can assume that there is something there that's inefficient. Or, of course, if I see that something is not happening at all, then probably something has happened and production has stopped. Moving on a step further, instead of just monitoring, we can also assist the person doing exactly that same task, again in this case using mixed reality, by bringing the actual model in front of his work environment and allowing him to build using directly the model. Now, just to explain what massive difference this can do for the worker, in the previous project, we had measured that in the case of steel fixing, workers spend about 60% of their time reading drawings and measuring. As you can imagine, I don't need to do either of these things in this case. So I can easily make a person twice as productive simply by allowing him to build in this way. Of course, you can always go further. This is what I call assisting plus plus and the concept of robotic teleoperation. This is work together with a colleague at Cambridge in evolutionary robotics, Fumiya Ida. I'm assuming some of you may have seen that movie playing in the bottom, Real Steel with Hugh Jackman. If you haven't, it's a really good movie. What you see here is basically someone pretending to be boxing, but he's not actually doing the boxing. It's the robot that's doing it for him. This is a clear, simple case of robotic teleoperation, where you're monitoring a person's motions, transferring that to a robot, and then bringing back what the robot sees and feels to allow that person to better remotely control that robot. Well, when I watched that movie, I started thinking, well, why can't we do this with construction? Instead of a boxer, why not have a worker and allow that person to be monitored in the office and then those motions transferred to the dangerous construction site so that the robot can do the work with, of course, a lot more safety for him. A very early prototype of that is what you see here. Very simple case. We have, as you can see, a student in the back capturing all their motions down to the fingers. And then through that, we allow him to control this brick building process, picking up bricks, picking up a spade, placing mortar, picking up a hammer, aligning the bricks, and so on, without him physically touching any of these tools. Another example, to take that a bit further onto the operation and maintenance phase, I will return back to mixed reality, another project we did on bringing digital twins on top of the real world. What you see here is a development we did on top of Microsoft HoloLens, where we're actually detecting the floors, the ceilings, the walls, and using those detections to further refine the registration capabilities of HoloLens so that you get a much, much smoother motion as you are walking across the room. Another example of this for the case of bridges, this is the actual digital twins of bridges with the real textures and the real problems, where now, once we have this data set, we can bring that to the office and allow an inspector to walk around and visualize the problems and do a bridge inspection right there. Or you can bring exactly the same data set in a VR environment and allow that person again to do typically exactly the same things he would have done on site, only this time do that within the office in a much more comfortable environment, which is also great for training younger inspectors. The last example I'll mention is related to asset protection. It's an example actually that's very simple but very powerful. In the UK alone, a bridge a truck hits a bridge, I believe that's every 4 hours. That's because, at least in Europe, but also quite a lot in the US as well, we have quite a lot of assets, old bridges built in the 40s, 50s, and 60s, back when the trucks used to be a lot lower. Now the trucks are higher, but the bridges haven't grown. And so the consequence is we have a lot of low height assets, and a lot of the truckers are not aware of this information, hence the concept of bridge strikes. If you Google bridge strikes online, you can find tons of examples of very, very dangerous accidents that have happened as a consequence of this. There are solutions to this, active solutions with permanent infrastructure and laser beams. However, those solutions are so expensive that the feedback we get from owners is, I'm not paying for that. I'd rather let the drivers keep hitting. So what we try to do is try to come up with a solution that's orders of magnitude cheaper so that it would be worth it for them to install it in more bridges. And this is what you see here. Simply using a camera placed further upstream in traffic allows us to capture the overhead vehicles by exploiting the concept of the overhead plane. Basically, if you mount a camera exactly at the height of the overhead plane, you would expect that roughly that plane appears as a line in your view, so your camera then works like a laser sensor. But then from the same camera can also capture the license plate of the offender. And if we provide the warning and this truck doesn't take an exit and continues and actually hits the bridge, then we can use accelerometers to detect the hit, link that with the license plate data and the warning, and then send that information to the bridge owner so that they can take action if necessary. You can see here the concept, very simple concept of mounting the camera at the overhead plane and then using features in the video to detect any object that is passing higher. Anyway, so I'll stop here and acknowledge the fact that I didn't do the work. It was the people that you see there in the bottom, and the ones above it were the ones that paid for it. And to stop here and say thank you very much. This is, by the way, our in-house software that we use for a lot of our work called Gygex. I call it MATLAB on steroids because what it does is that it allows you to visualize as well as manipulate point clouds, building information models, images, videos, all in the same space, while at the same time it is linked directly and natively to OpenCV, to PCL, and various other libraries that allows you to use their power to do quite a lot of interesting stuff. That's it. I try to keep it simple, no equations, no nothing. Go ahead.
So you mentioned drawing information from sensors to detect the conditions of these things. Is it also possible to infer the physics or the structural behavior of bridges, buildings, etc. from scans? Or are there, would you have to know how it was constructed to be able to infer?
So this has to do with going further down the level of detail path. Basically, what you can get from points and pixels is only what's on the surface, what's visible. If you want to go deeper and understand what's happening inside the components, you can, of course, infer it. But if you really want to know, then you have to use other kinds of scanning solutions like radar, sonar, and so on. There are a lot of discussions going on about how we can use the concept of 3D medical tomography, where you're scanning multiple sections of a person, and then you're bringing those sections together, knowing how a typical human body is constructed, to assume the in-between in the buildings and bridges environment. But that yet is just a thought. It hasn't been practically applied, whereby we can go to a building and scan multiple sections and do that kind of work. Our thinking is that we're trying to get the lower level of detail first, the objects, the visible ones, and once that's in place, then the obvious next step is let's go further and detect what's inside.
So you're visiting a big group of geometry researchers in the computer science department. What problem do you need us to solve for you?
All of these. A lot of the problems that we have are, as you can see, related to geometry. We have a lot of problems in terms of detecting objects. That's not a solved problem yet for many of the assets, okay? And creating those geometric digital twins. We have problems in terms of representation, compression. How do I best represent this information so that I maximize the information value while minimizing the redundancy of data? There's also quite a lot of problems within that space relevant to how the geometry interacts with every other type of data. Because in essence, at least from my perspective, the geometry is kind of the linking core on top of which you bring in, for example, the sensor data, the crack data, all the other problems. And without the geometry, you cannot make sense of all the other stuff. You have to be able to provide that correlation and understand that if a crack is in that position with that orientation, it means something very different than if it was somewhere else. There's also interesting problems that have to do with learning how we build things. Think about applying machine learning to the nature of architecture. Okay? Yes, buildings are different, but they're not that different. They have a certain degree of similarity that I think can be learned. And from that, we can use that learning to inform many other processes. Same thing for bridges, same thing for roads. You see quite a lot of repetition and similarity that, if learned, can be used for multiple applications.
So you mentioned learning. Do you like problems in this domain and needing a particular type of learning? Like, where do you get your data? And if you're, unlike a lot of these problems in computer vision where it's enough to say like car, human, sign, here you might need a very particular engineering, widget that you have to buy from a specialized place. Where do you see the interaction between the sort of fine-grained engineering problems you have and the learning aspect?
Clearly, there's interaction in the tool sets because, of course, we start with what's already there and see whether we can use more simplistic tool sets to solve more complex problems. In some cases, it works, and then that's great. In some cases, it doesn't, and then there is a challenge of how we can provide perhaps some additional intelligence on these tools to solve the problems. To give you a simple example, it's the concept of the simple white wall. If I have a white wall and I give you the points and the pixels of that wall, what do you see? Well, it's just a white plane. You don't know if that white plane belongs to a ceiling. You don't know if it belongs to a wall. You need the context. A very simple example that shows the value of context in that case and the reason for having to learn how the environment works with itself so that we can better use it for learning examples. On the types of learning systems, I wouldn't be the right person to ask that. I think you would be the right person to ask that. And then this is why we're here. This is why we're trying to work with you guys to understand, given the particular details of a problem, what kind of learning mechanism would best fit to address that type of application. This is where we mostly need your help. And I think there's quite a lot of opportunities there. As you can see, there's many problems, several of which we've only started to solve, but we're very far from actually solving them.
Any questions for Ioannis?
Do you have a strong reliance on your priors when detecting these features for bridges, buildings, and so on? Like, for instance, if I would run the same algorithm on London Bridge, would it also detect the fine features of the bridge, like the statue and so on? Or, God forbid, I run it on this building. The weirdly angled walls, the
Well, there's many parts to an answer I can give you on this. So the first part is, where do you actually need these tools? And my answer to that is, typically you don't need these tools on the very unique, one-of-a-kind assets. You want them on the very repetitive, high-volume type of assets. So in other words, if I have a very unique bridge, okay, that's a lot of work, but it's one bridge. I can sit down and get the work done manually. The problem is when I have thousands and thousands of highway overpasses that are pretty much quite standardized, and those things I want to automate, right? Same thing for a building. MIT and its campus, and likewise Cambridge and its campus, and some of those buildings, yes, they are unique, but the vast majority of buildings are not really unique, no matter what the architects may claim. Okay? And so it's those kinds of buildings where automation can have a massive impact. So we start with doing those things first, and then try to explore the more difficult cases, like rooms like this one with slanted walls and weird ceilings. Did that answer your question?
Yeah.
Okay.
All right, well, if there are no more questions, let's thank our speaker and,